Hi, I'm Dan Blanchard. I work at Parsley. I am a back-end software engineer there, and I'm here to talk to you today about simple, reliable parallel processing with Python and Storm using Streamparse and PyStorm. So just throwing out lots of proper nouns at you just to keep you on your toes. So as most of us are well aware, Python has this lovely thing called the global interpreter lock, or the GIL, which makes it so that you can't actually run two pieces of interpreted Python code at the same time in the same interpreter. So even if you use multi-threading, it won't actually gain you any performance benefits unless one of your threads is waiting for I/O. If you're trying to do two CPU-bound things at the same time, you're out of luck. On multi-core, it can actually even make your performance worse than your single-threaded application. That should be fixed in Python, I think 3.2 or 3.3, I can't remember, whichever the one they rewrote the GIL in. But for Python 2, if you're stuck on 2.7, that is really awful. Anyway, my lovely boss, Andrew Montalenti, discussed this in more detail this afternoon. If anybody went to his talk, I think it was at 1 o'clock. But moving on. So the standard way that most people try to solve the problem of the GIL with a large production system where you're trying to do lots of things in parallel is by using a queue and worker system where you have a queue that sits there and fills up with jobs, and then it sends the jobs out to the workers. So most people who do this use things like ZeroMQ and Redis and RabbitMQ and cron jobs and RQ and Celery and all that. I say this because before my time at Parsley, this is what the architecture used to look at Parsley in 2012. It was kind of a mess with all the workers and queues and things feeding into each other, and they thankfully before I came, they decided that was really messy and that it was time to try to move on from that. So it was around that time that they heard about this thing called Storm. And like, what is this? So it's the tagline is that it's a distributed real-time computation system, and so if you read that, you go, okay, well, what does that mean? But the basic idea is it can allow you to really simplify your setup of workers and queues, and its Python support out of the box is not the best, but it does allow you to add support for basically any other language to Storm pretty easily through this thing called multi-lang protocol, which we'll talk about later. And so what we've done at Parsley is there's a project called Streamparse, and now there's a sort of offshoot of that called PyStorm that are here to try to make working with Storm with Python much simpler. So as a bit of background, I should mention what we're actually using Storm for. And so Parsley is a web content analytics platform for major publishing companies. So that's just a small list of our customers. There are many more. And basically what we do is we provide these really nice dashboards for editors and writers to look at every day that show them things like how many views or minutes of engaged time, or what are the most popular articles on the site, who are the most popular authors, that kind of thing. And editors and publishers love that because it allows them to actually get an idea of where they should be spending their money as far as what are the kinds of stories they can do that'll actually help them make some ad revenue to stay afloat. We also provide some powerful data APIs so that people can do recommendations and things like that. So like the New Yorker's You Might Like thing uses the Parsley API under the hood to recommend pages you might like. So that's a lot of data that we deal with because we have so many publishers. We're talking billions of page views we're dealing with every month. So one of the common things you hear from people is that, well, Python can't do this. It can't scale. It's just a toy language. It's the kind of thing you'll hear from Java people about this kind of stuff. And or should have used Scala was one that you might hear occasionally. But we've found that using Storm and Python together, it's kind of hard to see that on this display, but basically what this is showing is that this is like HTOP running on 3 different servers, and every core is lit up pretty much 100%, all from Python processes running in parallel using Streamparse. And that's all thanks to Storm. So Streamparse is basically what allows you to do Pythonic Storm. It lets you parse real-time streams of data, which is the idea behind the name. It smoothly integrates Python code with Storm, and it's got some nice tools for getting started, and it's heavily production tested. And I was wondering why my animations weren't working, but so it decided to work on that one bullet. So that's awesome. It's good for lots of low latency stuff like analytics and logs and sensor data. So in this talk, basically, I'm going to outline some basic concepts behind Storm and topologies, talk a little bit about the internals, because it's kind of interesting, and then talk about how we actually get Python to work with Storm, talk about how Streamparse kind of came about and what the state of things are and where we're going next. And if you want to follow along at home, the slides are available at the URLs listed there. It's basically parsley/slides/PyStorm 2015. So the basic concepts behind Storm. So Storm has these abstractions for data processing. Primarily, we've got the tuple, which is like a little chunk of data. Then you've got spouts, which produce these tuples or chunks of data. Bolts, which take the tuples and process them in some way. And then you've got topologies, which are how everything connects all together. So as an example, with this wired topology, you can see that we've got a spout over here that's producing some tuples. These little lines represent the streams of tuples that are connected to different bolt executors, because you can have many different copies of the same bolt running at once, and, running on multiple machines to keep up with the flow. And bolts can even feed into other bolts. It's not so you can have a very complex topology. The basic idea behind a tuple is it's just like a Python tuple. It's just a simple list of data, a sequence of data, I guess, not list, right? And so in the first one we have is basically just a tuple that contains words, and the second one is a tuple that contains words and counts. The reason I'm using words and counts is because the word count topology is like the example you see everywhere for getting started with Storm and things like that. It's just, everyone loves to talk about word counting, probably because it's a really simple thing to, that'll fit on a slide. So a spout, as I said, is just a component that emits raw data into the cluster. And what we have here is the actual code that for using Streamparse to implement a simple spout that will produce an endless sequence of words. Granted, they're just dog, cat, zebra, and elephant over and over and over again, but it's a sequence of words nonetheless. As you can see, it's pretty short and sweet. We've got this initialize method that's for setting up connections to databases or initializing things like that. So in this case, we're just setting up this itertools cycle, but in a real spout, you might have something that's connecting to some sort of data store. Then you also need to implement next tuple, which is basically what Storm keeps calling over and over and over again to get the next tuple. And that emits the tuple on one of the streams. And then a simple word counting bolt we have here. Again, we have something that we're initializing here, a simple counter. And then there's a process method that you need to implement that takes a tuple and does something with it. In this case, you can see that we can access the values by name, which is something new in newer versions of Streamparse and Storm. You used to have to do everything by index, and so you'd have to keep track of what index all of your fields were, and that was really irritating. So we get a word, we increment the counter, and then we just log that just for debugging. And one of the things that's you might be thinking about this is like, well, if you're doing this all in parallel, how are these counters going to stay in sync and everything? So this particular implementation relies on something called a fields grouping. And so I'll show you how you set that up. So this is the current way in Streamparse that you'll set up an actual Storm topology. A Storm topology is just a directed acyclic graph that connects the spouts and the bolts together. You used to have to write really gnarly closure code to lay out your topology, which I was not a fan of. And so when I took over as the maintainer of Streamparse, I tried to make getting rid of that really high on my list of things to do. So I am happy to say that now you can write something really nice like this, where you basically, the classes that you've implemented before, like the spouts and bolts, they have this special class method, .spec, where you can pass the options that you want for the topology. So in this case, the par equals 2 means we want to have two. This is describing the parallelism for this component. So we want at least two, not at least, we want exactly 2 executors for this spout. And then the word count bolt has parallelism set to 8, so there'll be 8 of these running somewhere on your cluster. This inputs dictionary here maps from the source to what kind of grouping you want to use. And so here we're using a fields grouping, and we're grouping on the word field, which means that anytime a word is emitted by this spout, it will basically be hashed, and then that will determine which one of the bolts downstream it goes to. If since there's 8 of these executors for the word count bolt, only one of them will ever get instances of a particular word. So that way the count will be accurate, because we're just basically keeping track of one, well, not one word, but particular subset of words for each executor. So to kind of sum all that up, the way things look for the word spout and this counting bolt we have, the spout doesn't take any sort of input, not as far as the topology is concerned, whereas the bolt takes input from the spout, and the spout is outputting to the count bolt, whereas the count bolt isn't outputting anywhere. The types of tuples that we're going to see from them, for the word spout, it's just words, and then the count bolt, it's words and counts. And you can see that we've got this word fields grouping, again, on the word spout, but we didn't explicitly set up anything downstream from the counting bolt, but if we did, the default grouping is what's called the shuffle grouping, and where it just picks a random executor every time. So no particular instance of anything downstream would get the tuples from this. And again, we have the parallelism set to 2 and 8, respectively. So to sort of briefly talk about how Storm performs its magic, there's this thing called the tuple tree, and that's a little blurry, unfortunately, but the way it makes sure that everything is reliable is that every time there's a tuple emitted through the topology, it keeps each component along the way is supposed to send a special message, an ACK message, back to the Storm. The head, the master node, is called the Nimbus node. So it sends a message back to Nimbus saying, I have finished processing this particular tuple, or I have failed at processing. And so as that's going along, it builds this tree of how far along a particular tuple has been processed. So here you can see a bunch of words, and here's words and counts. So this is kind of give you a basic idea of what a tuple tree would look like. If something goes wrong along the way, Storm will automatically try and have your spout replay a particular tuple, so that way it can, try to pick up where things were before, and hopefully whatever that issue was just an ephemeral thing that'll go away. But either way, it keeps track of the state of every tuple that's processed. So as I mentioned, the master node runs a process called Nimbus, and then the other nodes on your cluster would be worker nodes, and worker nodes typically have a supervisor process and then a bunch of worker processes, and the worker processes are what are actually going to run the instances of your particular spouts or bolts. The supervisor just makes sure that if one of these processes dies, a new one gets created, and it also keeps in touch with Nimbus to let Nimbus know that this particular machine hasn't gone down. Because if you have a big enough cluster and you lose a machine, Storm is actually smart enough to say, oh, well, that one's off, so send all the work over here instead. And so it's really nice for providing high availability. The master node and Nimbus also provides something called the Storm UI, which is just a web view that lets you kind of see the state of the cluster, and it's pretty nice. You can click around and see logs and all sorts of stuff like that. Since everyone has internet troubles at this particular conference, I did not make anything actually clickable in this presentation. So when you start up your cluster, you're just going to end up with a whole bunch of empty slots on the machines that are just waiting for work. And once you submit your topology to Nimbus, it's going to start actually filling in the slots on those nodes. And you can end up in a state where you've got all of the processes for a particular topology all on like one machine, just by bad luck. If you've submitted like a whole bunch of topologies, it might just be like that's where the particular open spaces were at a given time. So one of the nice things that Storm has is this rebalancing command where you say rebalance, and it shifts everything around and makes sure that there's like an equal number of processes for each topology spread throughout the cluster. As a quick aside, if you're going to use Storm, you should use this book because Stormflight is a fantastic reference for using Storm. It doesn't have much about specifics with Python, but Andrew actually wrote the foreword for it, so we endorse it heavily at Parsley. I'm not actually going to go into the details of this particular slide, but if you are following along at home and want to read this in detail, this is basically laying out how Storm does some really fancy stuff to make sure that it doesn't run into network throughput issues, and how it detects like if it's running into problems sending messages to a particular node, how it shifts them to somebody else. So to sum up, Storm is pretty amazing. It guarantees processing via these tuple trees. It allows tuning how much parallelism you want per component in the topology. It's highly available, and it allocates actual Python process slots on physical nodes. We can rebalance things when things go a little wonky, and it handles high throughput network messaging automatically. And because of all this, we can use this to sidestep the GIL. So let's try to set something up so we get into a situation like this. So to actually get Python on Storm, we had to implement something called the multi-lang protocol. It is basically a simple JSON protocol that works via these shell-based components. So in the Java end, there's a thing called a shell spout and a shell bolt that Java has running that keep a pipe open to a Python subprocess. And so they just keep talking. They send messages to each other. So anytime there's a tuple incoming, it first has to go through the Java shell bolt like parent process, and then it goes to the Python process. So yeah, they communicate over standard in and standard out. It's kind of Unixy way of doing it, but it's also pretty clean. The nice thing about the way this works is we can use CPython or PyPy. We don't have to use like Jython or Py4j. I don't know if anyone here has tried to use Spark before, but using Py4j with Spark can be painful at times, because if something goes wrong, you get some sort of horrible, weird Java error that you have no idea how your code could have possibly caused this to happen. I speak from experience, like pulling my hair out trying to solve one of those problems for a while. So this is nice because we can just use regular Python and talk to things over pipes. And Storm has pretty extensive logs, and we have extensive logging on the Streamparse side. So if something goes wrong, you can pretty easily pinpoint where it went wrong. But it is a little bit of a quirky protocol, but it's not too hard to implement. So as I mentioned, there's these shell spouts and shell bolts, and they talk to things via standard in, standard out using JSON. One thing I want to mention is that in recent versions of Storm, they've added support for doing this serialization. They made the serialization pluggable, so you don't have to use JSON anymore. It's just the person who's written the multi-lang client for your language must have also implemented, whatever protocol you want to use. So, and in our case, up until very recently, there was nothing that supported anything other than JSON on the Python end, as far as talking to multi-lang is concerned. But in the upcoming version of Streamparse, we're adding support for message pack, which was first developed by, well, I'll get into that later. Anyway, so there's one subprocess per Storm task, and so if we set the parallels into 8, we end up with 8 Python processes. So you never have the issue where there's Python threads at play. There's also some nice extra stuff that if you want to make a really fancy topology, when the connection between Java and Python gets set up, there's this handshake that gets sent, which has a bunch of information about the topology, like what are the things that are feeding into your component, what are the things that are reading from your component. You can even store settings for your bolts inside. There's like a big config file, basically, that Storm keeps track of for each topology. And so you can put your own custom stuff in there. And it's a nice way to be able to distribute settings to all of your components. It also recently added support for heartbeats. So if the subprocesses get stuck, that'll be detected. If you're using Storm earlier than 0.9.3, they did not used to be detected, so you could end up with a really awful state where it looked like everything was fine with your topology, but for some reason it just wasn't doing anything. So that was a great addition recently. So there's this thing called storm.py that's bundled with Storm, and as a newbie to Storm, you might be tempted to go, okay, well, Storm comes with this thing. Why do I even need Streamparse or any of this stuff? Well, it's not to be confused with PyStorm, which is something I'll talk about in a minute. It's not at all Pythonic, and it's really unreliable. There is like no error handling at all in it. It is just it was written by a bunch of people who didn't know how to write Python. It was written as an example very early on in the project by a bunch of Java developers, and it looks and reads and acts like that. They also have a Ruby one. I don't know if that's any better, but the example ones they give, I think, were really intended as examples, but people started trying to use them in production, and that wasn't really a great thing. So, partially we thought, well, we should fix this. We should make it so there's a decent implementation for Python. So it'd be nice to be able to treat Storm as an infrastructure, like how, even though Cassandra and Elasticsearch and things like that are written in Java, a lot of people here use them because they have really nice Pythonic APIs you can use to access them. So Python needs to be, a first-class citizen for this. And one of the things when you're submitting a topology to Storm, it has to be in a jar and all that. So it'd be really nice if we could wrap a lot of that so you didn't have to worry about how to put that jar together. So now I'm going to talk more about Streamparse and how we sort of solved some of these problems. So the initial release was in April 2014. It's had over a year of very active development. We've got, I updated this number today, over 800 stars on GitHub. It was much lower before. And it was a trending repository in May 2014. We've got a lot of active mailing list members, and we're up to 13 non-Parsley committers. And there are 3 Parsley engineers, myself included, who are maintaining it. I'm the primary person these days. And we've even got funding from DARPA to keep maintaining it, which is nice. I think for like another year that's supposed to continue. So if you click that link, you can see the project description and stuff for why they're funding this. So after Streamparse came out, it was only a matter of months later, I think it was maybe like 5 months later, that Yelp came out with this thing called pyleus, which is their Python Storm library. And we each take different approaches to handling some of the problems with packaging and how you should describe your topology and stuff like that. So I think there's a place for both of them. It just depends on your particular preferences. But the part that doesn't make any sense is that we're both implementing one part of our projects is we're both implementing the exact same protocol, this multi-line protocol. There's really only one way to do it correctly, and we both wrote the same code independently. Like if you did a diff on it, it was almost identical. So we should really just have one Python implementation of multi-line, because anytime they add new features to this protocol, like why should two different sets of developers have to go in and update it and test it and all that? It just seems like a giant waste of resources. So enter PyStorm. What PyStorm is there was a sub package inside Streamparse that handled the IPC stuff. And I split that out into its own project. I even made it in a separate organization on GitHub, so it doesn't look like it's owned by Parsley. It's just PyStorm/PyStorm on GitHub. And then I took the pyleus serialization code, which was the only thing that they had that was different from us, and I put that in there. And so it's like completely backward compatible for their end. And then I submitted an issue to them and said like, hey, why don't we work together on this? That'd be great. And I heard nothing. But I'm hoping that eventually, I think people get busy, right? So they're probably just busy. I totally get what being busy is like. I'm not trying to like publicly shame them or anything by bringing this up. I'm just saying, hopefully someday they'll get around to responding to that issue. And I would really like to see this replace storm.py in the Apache project. I also know that the main developers of Storm would also like to see this replace storm.py because they don't want to keep maintaining it because they don't know Python. So hopefully we'll get there, but we're not there yet. So I guess I should mention, so right now, the in-development version of Streamparse, it has a dependency on PyStorm instead of just having its own copy of it. So I might, I mentioned Streamparse and PyStorm kind of like almost interchangeably in this talk, but PyStorm is basically just the subsection that deals with multi-line directly, and then Streamparse has a bunch of extra stuff on top of that. So Streamparse provides this command line interface called sparse or sparse. That's front end, and you can install it with pip. You can install this whole thing with pip, and annoyingly right now you need this other dependency that's not pip installable called line again, which is like a closure thing. But once you have that set up, you can just run sparse quick start, and it'll give you an example project that just is a word count topology. And you can run it by running sparse run. You'll see a ton of debug output. Like this box should go down to here and then have dots after it, I guess, but I don't want to make it too obnoxious. We can see an example of this over here in a GIF. It's a little hard to see, but basically, they ran sparse quick start. They're running it. You can see over here there's some process monitoring, so you can see the Java stuff started up. Right now, it's compiling the topology, which takes a little while because, Java and compiling. And then for a second here, you'll see some Python processes all pop out once things actually start to happen. So you can see there's a bunch of Python processes, and then unfortunately the GIF loops. So when we run sparse, so to run that'll run it locally, right? So this is for debugging. There's like a local topology mode where you're running it all on your machine. You can see everything there, and if something goes wrong, you can pretty easily track it down. If you want to actually run something in production, you need to submit the topology to Nimbus. And so the sparse submit command does a bunch of stuff for you. It'll make virtual ends on all the worker nodes in your cluster that have all the dependencies your topology needs. This is optional, though. We recently made this optional because some people were in situations where, they didn't have SSH access to the boxes that they were submitting to. The only port that was open was the Nimbus one, and so they said that we're going to manage our dependencies on our own. Is there some way that you can make it so you guys stop trying to install stuff through SSH and having it keep failing? So we added that, and then after that, it builds a jar. It's specially formatted jar with your code in the right directory to make Storm happy. It tunnels into Nimbus, and then it constructs an in-memory topology spec. and then it uploads everything to Nimbus. So that's a lot of stuff to have to do yourself. It's nice to just be able to run one command and not have to deal with it. One other thing we provide is this thing called the batching bolt. So in this case, this is using a couple new features, but you can specify config options to the topology like this now. And so this is talking about how tick tuples. So one thing that they added in Storm is, OK, 5 minutes. Tick tuples are basically tuples that come every so many seconds. So you can set the frequency in seconds. So if you want to have something time-based going on, the cleanest way to do it without having to actually add threading and a bunch of stuff to your code, which is kind of the whole thing you're trying to avoid in the first place, is using tick tuples. And so it's just a guarantee that you'll keep getting a tuple every so many seconds. So this says that we're going to batch things up into, for every 5 seconds that goes by, we're going to create a batch. And we're going to group things into batches based on words. And then we'll process a batch of words at once. So we're going to determine how many words were in this particular batch, is all this simple bolt does. So this is 5-second micro batches. And the reason you might actually use this in real life is if you've got some sort of crazy ETL topology where you're doing a bunch of transformations on your data from a source, and then eventually you want to load it into a data store, which is what we do at Parsley. So we get the raw data from, I'm not going to go through the whole infrastructure, but basically we get raw data, and then we do a bunch of transformations on it, and then we store it in Elasticsearch in the end. If we were just hammering Elasticsearch, sending it like individual document updates when we're processing millions of documents every minute, that would be crazy, and it would be really, really slow. So instead, we have a batching bolt that batches things every so many seconds and sends one big request to Elasticsearch at a time, which it's much happier with. Databases don't like to be hammered like that. So Streamparse and PyStorm sort of completely replace your need for using storm.py. There's a whole list of kind of snarky things on here, so I don't need to go through them all. It's just reiterating stuff I already said before. Basically, the config files we have, oh, right, I have a microphone right there. The config files we have allow you to even set up multiple environments. So if you have a Vagrant VM maybe on your machine for testing stuff out, you could have that set up as an environment with a Nimbus stored in Vagrant, and then you might have another one that's an environment that's actually like your production environment. So you can do sparse submit to each of these environments separately pretty easily. There are a ton of commands for sparse now. I didn't have time to mention all of them. Some of the newer ones that are nice let you get stats about the topology, the running cluster, and find out what your logs look like and stuff like that. The more exciting stuff is what's coming soon. So we're trying to simplify the deployment process. So currently we're creating all these virtual envs via SSH optionally, but that's how we handle dependencies. That doesn't work at all for Docker because people can't SSH into Docker containers typically, considering that they tell you to never enable SSH on a Docker container. So what we're going to try to do instead is set it up so that once the topology actually starts up, it's going to then run this one-time process that sets up your virtual envs. The Python topology DSL I showed you, I'm almost done. The Python topology DSL I showed is basically finished, but it's not actually available in a release yet. So the nice clean thing I showed you is in this pull request if you want to follow it. I also want to remove all traces of closure from our code. That should be pretty easy because we can use Thrift to communicate with Nimbus because Storm was designed to use Thrift. But we weren't doing that before because ThriftPy didn't exist. And ThriftPy is a really, really nice Thrift implementation for Python that is much nicer than the official one because it works for Python 3. And you don't have to compile anything to use it because it's all pure Python. It can parse Thrift files in pure Python. And then we're going to add message pack serialization from the pyleus people. And are there any questions? Can we squeeze one or two in? Right. No questions? Any? OK, thanks.